working on and was recently published to the Numenta community site. This is an effort to integrate one of the implementations of HTM with a popular emerging streaming framework from Apache called Apache Flink. I'm going to tell you a few words about Apache Flink because you may not have heard of it, but it is similar to Apache Spark, but it is intended for distributed, real-time stream processing of information like from Kafka or HDFS, and you do it on top of Yarn clusters or as standalone clusters. And what I'm going to walk through today is a project that allows you to use HTM to do anomaly detection of information as it flows through these distributed streams. When you're working with HTM, it's a library, and you're likely going to integrate it into maybe a big data solution. These are the kinds of problems that you might face when doing that. You might need to, I need to aggregate my data before feeding it into an HTM network. Or I need to build many independent models in a distributed environment, at high scale. Maybe I want to connect to a Kafka data source or drive outputs to an HDFS data sync. Maybe your data is coming in out of order and you'd like to reorder the information as it enters into HTM, since causality is very important when you're doing temporal learning. And finally, maybe you need reliable stream processing. After all, we might be doing this in production. We care about checkpointing and reliability mechanisms. And so with that, Flink becomes a very interesting complement to HTM. Because these are problems that Flink is designed to solve. I'll say a few words about Flink itself now. The project is a top-level project from Apache. It just reached 1.0. And it was a research project that was first developed by a consortium of German universities funded by the German Research Foundation. And there is a startup that commercializes Flink named Data Artisans in Berlin. Now, these are some of the features that people talk about with Flink. Flink provides a programming framework where you write jobs or programs similar to Apache Spark or Hadoop MapReduce jobs. Only you use the language of Flink, the APIs of Flink, and you do this with Java, Scala, or Python. Flink provides features like a distributed data flow graph, meaning that you describe the problem you're trying to solve, and then Flink's optimizer deploys an execution graph on some cluster to execute this streaming processing. It works with unbounded streams, meaning that the app never quits. It has very powerful reliability and statefulness primitives within it. So, for example, the HTM network is, of course, a stateful entity. It's accumulating state as it learns, and that's integrated into Flink's checkpointing and recovery mechanisms. So, if a worker node were to crash, we can actually recover the model that's being trained on another machine. There are extremely powerful data manipulation primitives within Flink. Flink provides windowing support, so you might say, show me, take this stream of records, and every 10 minutes I'd like to look at it, and maybe do some aggregation, or find the max value of this, or what's the average of that. It supports partitioning, and that's very important. When you've got a large-scale stream, it may be partitioned. For example, Kafka has a notion of partitioning. And with Flink, we can actually train numerous HTM models in parallel across those different partitions of the stream. It supports joins, so we can actually bring disparate streams of information together, and using time windows, we can join them in outer or inner joins, and those can become aggregate records that we then push into an HTM model. And finally, Flink provides iteration support. So the graph is a DAG that can have loops in it, so the output from something can become the input to itself. Now people ask me, I'm going to show you some pictures first of some of the things we just described. This is Flink's website, and they claim some big wins. Here's a depiction of this ordering problem where information that's arriving into your system might not be temporally ordered because maybe you're drawing information from different sites, and some of them have a laggy network. Sorry. So Flink can actually reorder those elements as they come into your system. This is a depiction of the data flow graph and some of the checkpointing mechanisms that it supports. I just want to give you a sort of a visual sense of what these graphs kind of look like. One of the really important differences between Flink and Spark streaming is that Flink deals entirely in what's called event time, which means when we construct windows, we say, give us the last every 10 minutes worth of data. This idea of 10 minutes is not meaning the clock on your server. It means look at the timestamps inside the messages, the records that you're ingesting, and organize the information in that way. So I want every 10 minutes in the event time domain. So Flink is a really amazing, I would say best-in-class streaming processing system. And while Spark is really great too, I love Spark quite a bit, and I've done a few projects in Spark and machine learning together. I think that HTM and Flink can be best friends because HTM is intended as a streaming temporal learning, and that just sounds to me like a great connection with Flink, and that's what we're exploring in this project. So I'm going to do a couple of demonstrations for you. I'm going to show you two demo apps that are included in the source tree right now. One of them is HotGym. Of course. We'll see HotGym in a minute. And we will see New York City traffic. Now I'm going to walk through, actually, I won't be able to write as much as I hope because I got a whole mic, but I'll show you a little bit of how we do HTM traffic, New York City traffic in Flink.
Would you like a mic stand?
That would be excellent. Thank you.
Give me a mic stand.
That's community support right there.
Hey, thanks a lot. Okay. So let's first talk for a minute about what I'm going to show you.
You can maybe go to the other side. Yeah, that is. Move the mic stand.
Thanks. Thanks again. Okay. So I'm going to develop, as quickly as I can, a little app that shows the use of what's called Riverview, which is a cloud source of temporal data that Numenta provides, and drive this data through a Flink data flow. What this picture just shows is that the Riverview service actually provides many partitions, or what are called streams of data. And what we're going to do is read those streams in parallel using a Flink data source called the River source, which is a parallelized source that can run at any scale. And then as it pulls in these strings, it will drive them into a set of HTM network instances. There will be one network instance per string. So we'll learn an anomaly score for each independent string. And this will happen throughout our Flink cluster where each network is processed in parallel. Finally, we'll aggregate the anomaly scores into a final result set using a projection function in Wright. Okay, so first thing I'm going to do is show you my traffic model. When you write Flink applications, using your own data types that come from your domain is very important. It's a strongly typed system and has a very rich type model. You can work with Scala case classes, which have pojos, tuples, and they're all typed. In my case, I want to work with a case class that I've defined called the traffic report. And the traffic report corresponds to some stream at some time, some speed, some travel time. I'm just going to quickly show you, if you haven't seen it yet, that this is the data source we're going to be drawing on. And this is the NYC traffic data source, and it's defined, as you see, provided by Numenta, and it defines the speed and travel time. And if I just show one of these streams really quick, you'll see that you get from the cloud a string of data that includes those timestamps and those two values as you see here. So first thing I've done is I've defined this case class to model that type of information. The second thing I'm doing is writing a network definition. And this defines the type of HTM network that I'm going to pass the information through. This is a very simple single layer, single region network. And because I'm not an expert in the use of HTM, this doesn't work very well. But it works for the purpose of my demonstration. And the other thing is encoders. When you deal with HTM, as you saw earlier, you must take data that comes from your domain and transform it into an SDR. The encoders are the way in which that's accomplished. And so you can see here I've used a date encoder for the date time, and I've used a scalar encoder for the speed with some parameters as need be. This here is the scaffold for a typical Flink job. What will happen is we'll create an environment object, which is the context object into Flink. And we're going to write a series of data transformations. We are constructing a graph. And when we finally execute the graph, the job is actually deployed and run at some scale on your cluster. As we said, we're going to create a river source using the traffic report type that you can find. And for the purpose of, for speed here, I'm just going to limit it to select strings in the list. But if you leave out the stream IDs already, you get all the strings. Now in this first step, I just want to see what the content of the star thing is. So I'm going to give this, oops. I'm just going to register this source with Flink, and I'm going to ask it to print all data. I'm writing this in Scala because Scala is wonderful. No offense to the Clojure folks that are writing their resumes. Looking forward.
But you're using the HTM Java HTML
Yes.
implementation.
Scala and Java are BFS, and you can use Java libraries all day long. But what you're seeing here in some of the network definition parts is a solid DSL for HTM Java that allowed me to write up network and encoder definitions much more succinctly than was possible with HTM Java. So what we found out of this output so far by running this job is a totally ordered series of traffic report elements as drawn from Riverview. And you know what I forgot to do is, I can show it here. Here I have an HTTP snooper on, and you can just see it that the river streams are downloaded like you would expect. So as you see, the elements are totally ordered, but the type information is used. So at all times you work in the native type system of the language that you're choosing, and it's just a really well-typed experience. Now let's get to let's actually do some learning. Now we define that network that I saw earlier, right? And what I want to do is select some information out of this network as it comes out. What's going to happen is one or more HTM network instances will be created, depending on how many partitions are coming from the underlying source string. And a series of inferences will pop out. And what we can do now is project the output however we see fit. In this case, what I'm going to do is produce a tuple, which is just a pair of information. In this case, I'm going to take the inferences anomaly score together with the original input, and this becomes the tuple that I'm going to emit out of this part of the graph. This is going to become my anomaly scores. Now, at each step here, what's being created is what's called a data stream. So if we look at the type information of this, and as we go, and at each step after that point, you can see that, in this case, this is a data stream containing tuples of the original traffic report plus the anomalies. We can chain these together as we like, and we'll do that in a second again. But let's just now, run this. You can see how my processors are all running because I'm actually training numerous models in parallel right now. And you can see from the output, which I guess we'll quit in a second, you can see there's different thread indicators on the far left. You can see that there are numerous models being trained. If I stop this, again, you're seeing anomaly scores on the far right, you're seeing a thread on the left, and with your eyes, I forgot to do something. Sorry. What I actually want to do is actually tell it that I'm training in a partition way. I actually need to tell Flink that I'd like you to take this stream and actually partition it in a certain way. So it doesn't need to be the stream ID. It could be some other property of that stream that I chose to partition on and train independent models on. I hope that makes sense. So when I run this again, I get what you would expect. Now you'll see a closer affinity between the stream IDs and the thread IDs because of how this is laid out. Now we get something closer to what I had. So let me jump ahead to another demo. Let's look at, number one, I'm going to show slightly more embellished form of the traffic demo. Okay, so this is the final form that you'll see in the source tree right now. This is something that replicates the end of the tutorial video that Matt put together. What you see is obtaining the traffic data from Riverview, creating what we call an investigation interval on August 3rd through 4th, and we want to find anomalous routes. So we assemble those anomaly scores, but I really only want to learn up until the point when I get to the end of the investigation. And And so I'm just filtering the reports up until the investigation ends. And then, I want to then take those scores and specifically call out the ones that are in the investigation time window, and I want to pick up ones that have significant anomaly. And so when we run this, we would probably expect.
I'll put it's the next speaker that gets it. Next speaker.
Okay, so now I'm going to switch gears a little bit and I'm going to look at HotGen. HotGen is very similar, and we won't spend too much time on the code this time.
Can you go to the previous one? I just wanted to know, what part is HTM? Dumb question. What part is HTM and what part is Flink?
Well, the way that these, this is like a fluent syntax that is typical to Flink. And you put operators into this syntax to make transformations over these data streams as you go. And it's a whole DAG of transforms, so it's not a single flow, but it can be many.
What's a DAG?
branch.
It's like
Thank you. Yes, it's a graph of transformations that can go in and out, and even, as I say, move back on themselves. So it's a very rich language for building these streaming flows. But to answer your question, at the point where we put this learn element, that's the point at which we've inserted an HTM operator into a certain point of the graph.
Show the network creation. Where you're putting together the HTM Java components that build the network. I think that's what he's asking, right? That network instance you're sending into the learn function, that's where HTM is. The date encoder, the creating the regions and hooking them together.
Yeah, so here let's switch to HotGen for a slightly more familiar example. Here's the classic network definition of HotGen, and again it has a timestamp and a consumption. And then at the point at which we actually ask it to learn, we have to supply the network as input. And many instances of this network will be created for every keys or partitions.
Excuse me?
Yes.
Where is learn? The learn.
Oh, yeah. If you maybe you can't see from here, but there's a little underline under the word learn, a little gray underline. That's IntelliJ's way of telling you that this is what's called an implicit conversion.
Oh, I see.
Scala has a capability similar to C#, where you can extend classes that you don't write, you don't own, with new functionality, and the compiler figures out what to do. So learn is actually extending the data stream to support anomaly
But
detection.
you haven't defined that the traffic model, right?
No. What happened was at the top of the demo, we import our Scala DSL for anomaly detection in Flink. And then what happens is this is some Scala goodness, but this is all. I should mention that this is all accessible to Java programs as well. The DSL elements notwithstanding. So if you just want to write Java code and you want to use HTM Java in Flink, that is perfectly fine. In that case, you use a static entry point into the HTM system. So I'm going to run this now on a Flink cluster. Let's just run our HotGen demo. Here I'm going to take just a line of text here that I'm going to run. And what it's going to do is it's going to read the hourly CSV that's classic to HotGen, and we're going to write out some anomaly scores. Now, this has some nice text output, but let's actually switch into Flink's UI. What you'll see here now is that Flink is showing that my cluster has 4 task slots, which means it's capable of running 4 things in parallel. This is actually what's called the local cluster, it's just running on my Mac. Flink has got deployment scripts for the various public clouds as well, and you can really scale this up. What we see is that I have a completed job here that just ran for 23 seconds. And it's kind of a nice little chart that they show. And this is a linear graph you see running from the comma separated file source through an HTM network, through to some sync, which is writing the code. There is some metrics in there as well, so we can see that our HTM stuff processed 4,300 records with a total millisecond time of 23,000 milliseconds. What does that mean per record? I don't know. About 5 milliseconds a record. And there was only one network created. So then in the end, you kind of get what we expect. So here we've emitted the classic common separated file containing the timestamp, the actual, the predicted, and the anomalies one. I'll take this. Thanks.
Thank you.
I'll just say a few more words about where this project will go from here. All right. So we walked through a day in the life of Flink job development. There's some important things to do next to make this really rock. Number one, the checkpointing stuff of Flink is so powerful, but it depends on the ability to serialize your state. Well, guess what? HTM Java doesn't support serialization today, but should and will to make this really work.
Just implement serializable and you're done, right?
Well, yeah. David and I have been chatting about how to proceed on that. He knows best what to do there. Well, we got to get it done so that we can have a totally integrated checkpointing system. When you read more about how Flink does checkpointing, it's going to blow your mind. Like, let's say you're drawing on a Kafka string and you blew up. Well, when the system recovers, the offset into the source Kafka topic is actually retained in the checkpoint data. So it will rewind back to where it left off in the Kafka stream. It can achieve exactly once processing of streaming information from Kafka through to HDFS. And when we get serializable HTM models, we'll be integrated with that checkpointing as well. All right. The river source actually quits when it reaches the end of the stream, but what I'd really like it to do is sleep on the interval that's defined in the source so that it just keeps running. Next thing, this is a pretty great basis, I think, to do swarming on HTM Java. Now, I would like to demonstrate the viability of that if I understood a little more about how to do swarming. After all, this is a distributed system that can easily stand up HTM model instances for us. And I do believe we could use that as the basis for swarming. And finally, I don't have support for network racing right now.
So quick question. Can't we use the Python swarming, module to get the data and integrate it?
Yes. Essentially, you hand code your models today. But there is obviously some interest in being able to do swarming on top of the Java library, and this could be a good substrate.
For a proof of concept, actually, it's already there in Python.
Yeah. So this was recently posted to the community site. Kind of just got started with it, but there's a little wiki that shows you how to run the examples and build this. Boy, I'd really like to get some contributions and see where this goes. Thanks again, everyone, for your time.